Thanks everyone for coming. This is a talk on complexity theory, particularly NP and non-determinism in general. NP stands for non-deterministic polynomial time. The term non-determinism in computing is, I think, it could use a better name, honestly, because it's somewhat similar to the concept of non-determinism that's a bit more familiar, but there are some very subtle differences. And honestly, there's also a number of other ways in which you can interpret what exactly is going on here. And this turns out to be probably one of the most interesting and one of the strangest aspects of computing. This is perhaps one way of kind of starting this out with explaining non-determinism. There is the class NP, and then there's another complexity class called P, which is where the vast majority of algorithms that humans write these days are, right? Most things that we build software out of are in P, and then NP is kind of this. People are generally afraid of using it because it is something that worst case can take exponential time, and that tends to scare some people off. In practice, though, it is a lot more nuanced than that, and there certainly are a lot of cases where it is more practical and more tractable than people realize. So there are a number of different ways in which you can kind of look at certain capabilities of a computer, and there are certain, to some extent you can kind of invent arbitrary ones, but there is, you can look at how long does it, what can a computer compute if you give it a certain amount of time? What can it compute if you give it a certain amount of space? And generally there are a lot of these hierarchy theorems where you can show that, if you have a computer that has a certain amount of time to finish something, and then you have a computer that has a longer amount of time to finish something, the computer that has a longer amount of time can generally solve a wider range of problems, right? And the same goes for space, although space is a little bit more complicated. But generally you have a lot of these hierarchy theorems. NP is a bit stranger, where there are actually reasons to believe, or there's actually a lot of evidence very strongly indicating that you cannot actually, a lot of these problems you can fit them into like this linear hierarchy of, you can kind of just have like a linear metric of how much time do you have, how much space do you have. NP is something where you don't actually have a linear metric. So there is a major unsolved problem in complexity theory of, is P and NP, are these two complexity classes actually different, or is there some secret algorithm we have not discovered yet that lets you solve NP problems faster? All of the empirical evidence very overwhelmingly suggests no, but it is an open question. It is also a very strange open question, because there's this thing that has happened in complexity theory where, People try to solve NP. It is, the P versus NP problem. It is arguably the largest open problem in the field, and generally considered one of the largest open problems in all of mathematics. And it's also practically extremely useful because it determines whether or not cryptography is actually something that can be secure cryptography is actually mathematically possible, or is there some secret vulnerability in every possible encryption scheme you can come up with. But NP is, it is, there's this thing that keeps happening where every so often, a bunch of these complexity theorists will come up with a bunch of different techniques for how they're kind of trying to approach the P versus NP problem, and then every so often someone comes up with some proof that shows that actually all of this wide diversity of different techniques people are trying are actually all secretly the same technique. And that actually here's a proof why this wide class of techniques can actually fundamentally never answer this question. And this has not happened once, it has not happened twice, it has happened 3 times already. there's a lot of very, very strange stuff going on with NP. So I'll dive into a little bit, more specific rather than talking about the abstract. NP, there's a number of different ways in which you can interpret it. One is if you have some computation, and if you have some computation, if you have some function, f of x or something, there's some finite range of possible values of x, and in most cases. And so the question, one way of viewing NP is you can try out every possible value of x at the same time, and find some kind of answer that way. And then another way of viewing it is that you are able to run functions backwards. So if you have some arbitrary function f, and you have y equals f of x, you can for arbitrary functions f, you can invert this where you can get some where you can solve for y, where what is like g of y that equals x, right? And so it's to some extent running functions backwards, and it's to some extent trying every possible combination at once. And I'm sure people have heard the pop science, quantum computing stuff. There are close connections between NP and quantum computing, but they are also distinctly different in a number of ways. So another way that you can, one interesting thing about NP, and this is something that there's the field of complexity theory largely saw a very large revolution after this was discovered. In 1975, I believe Richard Karp published his paper on proposing the concept of NP completeness. And NP completeness is a property of certain types of problems where they are problems that are in NP, and they are capable of emulating any other problem in NP. And NP is a superset of P, and so they are also capable of solving problems in P as well. The kind of canonical classical example of an NP complete problem is called SAT, or the Boolean satisfiability problem. The formulation of this is you have some collection of Boolean variables. Maybe it's A, B, C, D, so on. These are all Boolean variables. They can either be true or false, 1 or 0. And then you have some collection of clauses, and the way that this is, these are constraints, and these constraints take the form of generally, some collection of variables. The minimum that you need to be able to have for something that's NP complete is 3. If you have essentially like not A or B or C, this is an example of a constraint. This is generally you can invert. You can pick some arbitrary subset of these variables, you can invert some collection of them, and then you can put them all into an OR operation. So for example, this clause is true if A is false, or B is true, or C is true, right? And then generally you just have the Boolean satisfiability problem is you have some arbitrary number of these clauses, you have some arbitrary number of variables that they reference, and then you are trying to find some combination of variables that or some combination of states for all of these different variables that satisfies every constraint at once. So you have some in terms of logic gates, you are passing arbitrary inputs into either NOT gates or just passing them or passing them directly into OR gates, and then in terms of logic gates, you might have OR gate, some NOT gates are, and then you have some collection of these OR gates, and then they can all get passed into one big AND gate. And you're trying to make this output true for some combination of inputs. So this is kind of the canonical example of an NP-complete problem. This is something where it's very easy to convert arbitrary digital circuits into this type of problem. So an example of that is you have something called a Zeiten transform. This is just a bunch of kind of examples of ways of forming the gates. I'll kind of abbreviate the syntax a bit here, but if you have an AND gate and let's label the inputs A, B, and C, you need 3 constraints to define this, and I believe it's generally not A, not B, C. A not C, and B not C. And this is just, each line is all ORed together, the negatives are nots, and then each one of all of these together all go into an AND operation, and you're trying to satisfy all 3 of these constraints at once, and that defines an AND gate. Right, and then you can construct arbitrary circuits. Generally, if you are building some complicated circuit, you're not just representing the inputs and the outputs as bits, but you're also representing each wire in the circuit as another bit in the problem. So you may have a problem that that has only like a couple hundred bits of inputs and outputs, but actually it might be many thousands of bits for the entire circuit, because you have to represent all the wiring inside of the circuitry, right? There is some sense in which the input, the state space of this problem is still constrained to whatever the size of the inputs are, but there's a lot of nuance to this. Now, there's another way in which you can kind of interpret what's going on here, which is we can build up kind of a table of that's not dry enough right now. You can build up a table, and you can say, okay, you can say we're going to we're going to kind of build up a table. This, if you have n variables, this table is going to be like 2 to the n squares, basically. But this is, we're going to say, the x-axis here is a is, this is a is 0. This is a is 1. And then here we're going to say, B and C are 0, 0, 0, 1, 1, 0, 1, 1, and then we can just find places in this table here. So if we have these these constraints, so if we have negative A, negative B, and C, this is essentially A is 0, and so we can kind of fill in that whole column. B is 0, so we can fill in all of the squares where B corresponds to 0, and then C is 1, and so we can fill in all of the columns, or all of the places where C is equal to 1, which is all of this and all of this. And so that means that you have all of these, all 7 of these squares all satisfy this first constraint, whereas this one does not. And so this is an invalid. This is if we pick a value if we pick this value here, this invalidates this first constraint, and so that that is not a valid solution to this problem. Now then, if we have if we look at the second constraint, that requires A to be 1 or C to be 0, or C to be 0, and so that is that would essentially be if we make a smaller table here just to keep them separate for now. So A is 0, or no, A is 1, and C is 0, and so that would be here and here. So if you have, generally, if you have 3 constraints, you're essentially taking some state space and you're removing 1/8 of it. And if you have 2 constraints, then you're removing 1/4 of it, and so on, right? It's roughly by that that kind of exponential relationship. And then we have the third constraint, which is B and negative C, or B and not C. And so that is, we have, that would be B and, and B and not C. So C would be, or not C would be this and this. And so then, because we're doing this AND operation, so each one of these corresponds to one of the 3 constraints. And so then what we're looking for is what is the array of what is the range of values that in here that correspond to this AND gate. And so what we have to find the intersection of all 3 of these constraints. And so we just find what is a value that is, what are all the values that are in all of these. And so that's this whole first row. The second row is not compatible with this constraint. The third row, this part, this one here is not compatible with this one, and this one here is not compatible with this. And then I think actually, I might have made a mistake somewhere.
Not C, you filled in.
Yeah. In the second one.
The one on the top on the left.
Yeah, top up.
Yeah.
One on the whole bottom, trim them.
Right. So let me just. Let's see. That's. So B is, B or,
I think that one was
right.
But it's the one on the left.
But if I remember correctly, it is this last one. Yeah, I made a mistake somewhere, I think, but I don't know. I made a mistake somewhere, but essentially it corresponds. Like what? I'm not sure. One of these ones might. I think one of these ones might actually also be. I made a mistake somewhere in here, but this is generally it would be the ones that should be. The table that this should be is. So it would be the values that you would expect would be 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. So that would be there. All right. I think I wait. Let's see. A is
Can I?
Yeah.
Can I ask?
Yeah.
Because I may be less technical.
Yeah.
Than some of the people here. Can you give me an example of like the simplest possible Boolean? Like maybe n+1 that.
So I mean, like in terms of like a real world problem, or
Sure.
I mean, so I I mean, if you have a, kind of a, a simple kind of math problem, for example, would be if you have, if, you could, for example, define some math expression, and you can say, you could do A plus B equals C, and so generally you would encode these numbers in you'd encode your numbers in binary, and so that is for anyone not too technical, binary is instead of representing your digits as like 531 is equal to 5 times 100 plus 3 times 10 plus 1 times 1, basically, right? Thank you. Binary is, instead of using exponents of 10, you're using exponents of 2. So if you want to do say like 17 is equal to like 16 times 1 plus 8 times 0 plus 4 times 0 plus 2 times 0 plus 1 times 1, and so then you just kind of arrange these positions, and so that's how you would encode that number, and so then generally you might build some kind of circuit that implements addition, which is not particularly hard, but you have some number of these bits, which input bits, which correspond to each input number, and then you have some number of bits that correspond to the outputs, and so you can build out some kind of circuit here, and each one of these bits is essentially one half of the state space of the entire circuit. Maybe this is not the best explanation right now. I think as I kind of flesh things out a little bit more, maybe that'll help. So generally, you can, NP-complete, the class of NP-complete problems is, there's not just SAT, there are a wide variety of other problems that also have this property. So some other examples would be, some other examples of NP-complete problems would be, there is the decision variant of the traveling salesman problem, which is you have the traveling salesman problem is you have some collection of points and you're trying to find the shortest distance that takes you through every point, and then the decision variant is basically asking, is there a path that is less than this particular distance, right? There is some convoluted way in which you can encode arbitrary circuits to do arbitrary computations as some kind of array of points, and do and solve these problems with the traveling salesman problem. There's a number of other ones. Graph coloring is an example, which is if you have a bunch of nodes and they're connected in some way. If you say that you have some number of colors that you're able to color them with, and you add the constraint that two nodes that are connected to each other can't be the same color, you can say like, okay, this one is blue, maybe this one is blue, this one is red. Well, here this is something that is necessarily what's called three colorable, because you need a minimum of 3 colors for it, because any point that's here has to be a different color from this one and a different color from this one. Finding the minimum number of, or determining whether or not a graph can be colored with a certain number of colors, that is also NP complete. There's a number of other kind of more arcane problems, but I think Richard Karp's original paper on NP completeness listed something like 20 or 30 problems or so, and showed that they all can be converted back into SAT, and so they're all equivalent. But in general, if you have some arbitrary constraint problem, you have some problem. And there's some range of possibilities, and you say there is there's some range of possibilities, and then you say, okay, here is some property that this needs to have, and so everything that is not compatible with this property is all canceled out. Here's some other property that this needs to have, or some other constraint, and so we cross all of that out, and then we can add some arbitrary number of constraints, and we kind of narrow this state space down further and further, and then can you find some point that is in whatever is left over, and this kind of arbitrary constraint type problem is generally something that that shows up a lot in NP, or requires a lot of non-determinism in general. So yeah.
Can you explain why these problems require non-determinism? Like, why is there that asymmetry where it's sort of easy to verify that you have a solution and hard to find one?
Yeah. So I mean, to some extent, this is the big open problem. In somewhat. So actually, the specific case that is interesting is, let's say you have an AND gate. If you are running it forward and you have some set of inputs, let's say 0 and 1, well then an AND gate is only true if both inputs are 1, both inputs are true, and so in this case the output is 0, right? But let's say let's say that this is part of some much larger circuit. We're trying to break some cryptographic function or something, right? We have some cryptographic scheme where we're exchanging private information over the internet by like factoring prime numbers or something, and so we have some prime numbers like P and Q, and that we multiply them to get X, and we pass X around, and you can break this scheme if you know what P and Q are. This is a foundation of a lot of modern cryptography. If you could build up a multiplication circuit that takes P and Q and spits out X, and then if you could run this backwards, where you take X and you generate P and Q from it, this would break a lot of cryptography, right? So, we can look at a much simpler case of, let's say we have an AND gate. Can we infer the inputs from the output, right? So, in this, if we have an AND gate where we know that the output is 1, then we know that both inputs have to be 1, right? However, if we have an AND gate where the output is 0, we have some ambiguity. There are more possible outputs of this system than there are inputs, because this is essentially a backwards AND gate that has 1 input and 2 outputs, right? So if we have an AND gate that has a 0 as its kind of backwards input, there are 3 possible states that that we can have as an output. It can be 0, 0, 0, 1, or 1, 0. And so we essentially have this superposition of there are multiple possible values that this can have. And if we have some larger circuit, maybe we have some various circuits here, and then we have some circuit here, and it spits out a bunch of we have some set of outputs here that all kind of go to that all pass into these circuits. If we know if we propagate backwards some superpositions back to what are all the possible inputs to these 3 circuits that generate the outputs that we want, then the only, if they're all kind of coming from the same input, for example, then we actually have to, the only way that all 3 of these circuits can generate the outputs that we want, for example, is if the kind of superposition of these these circuits all happen to be exactly the if these kind of superpositions line up in a way where there is at least one value that happens to land in all of these superpositions, right? So if you're essentially asking, okay, what is the set of possible inputs that this circuit we can pass into this circuit to get the output we want? Same for the other two circuits. Is there overlap between these three sets, or are they disjoint where there is no possible input that we can get there's no possible value that this circuit can generate that produces the output we want on all three of these circuits at once, right? There are a number of that's kind of one example of why this is hard, because especially as if you have the number of possible inputs that you can have to each one of these circuits is 2 to the n, where n is the number of wires basically here, and so this can get very, very large very quickly. I believe the size of the entire internet is somewhere around like 2 to the 70, and so it does not exactly take that many. 70 bits of information is not a particularly huge amount of information, and so this is something that you can where you can very easily exhaust very vast amounts of computing power. For another number to throw out is if you have 2 to the 256th, this is about the number of atoms in the entire observable universe. And so having to track as many states as there are atoms in the universe is a little bit hard. One way I've heard people describe these kinds of combinatorial cryptographic problems is they are so large that describing them as astronomically large is giving way too much credit to astronomy. Let's kind of go into some other details. Anyone have any questions right now? Yeah?
So does it matter to know upfront how many constraints you are solving for, or you keep learning there are more constraints as you're figuring it out?
So that's an interesting question. So I think I would say that, and I'll give a little. I'll hopefully go into a little bit more detail on this later. I think there is a large extent to which neural networks, for example, are not always, but in many cases, learning problems that are that have some characteristics of NP. And so to some extent, what you're doing there is you have some kind of arbitrary circuit that you're trying to approximate, and you have some set of input and output pairs, which is essentially like I said, you have this big kind of plot, and there's some number of points in here that correspond to valid states, and so you're essentially sampling from these valid states and trying to reconstruct some kind of circuit that approximates this set of points. And so it is to some extent a problem. That is a situation where you don't know the constraints. You just know some subset of the solution space, and you are trying to generate a circuit based on that, right? I think that's a large portion of what people are doing with these neural networks. And if you have arbitrary sets of inputs and outputs, you can have weird non-deterministic structures in there. I think I had another point that I was going to make, but I can't remember it off the top of my head right now.
So is there like a minimum number of constraints you need to have?
I mean, you can have a system with 0 constraints in which every possible state is valid, right? You can also have situations where you have enough constraints that that there are no valid solutions. That is something that in the case of SAT is referred to as unsatisfiable. There are no possible inputs that are valid for this circuit, right? If you, for example, have a circuit that is that's implementing that's doing like multiplication, and you have like let's say you have you set this input to 5, the output to 12, and this is working over integers, and then you leave this value blank basically, and you solve for this. Well, there's no way of multiplying 5 by something to get 12, if you're just working with integers, and so this would be a situation where this is something that's unsatisfiable, right? Of course, if you have, you can, like I said before, you can have arbitrary constraint problems. If you have some, if you're talking about like, we have a rocket and we're trying to get to Mars or something. There's some, probably absolutely gigantic circuit that you could, some kind of gigantic mathematical function that is at least approximately equivalent to that, and you're trying to kind of sample that in some way where you can find something that satisfies all of these constraints. That would be another kind of example of a particularly hard problem of this kind. Does anyone have any other questions? Okay. Now I was saying before that these NP problems are oftentimes not as hard as they seem. They are oftentimes described as being exponential time. They can take a the cost of finding a solution here to some extent is equivalent to just checking every possible solution until you find one that works, right? And there's to some extent an inability to kind of reduce the problem beyond that. There are tricks that you can use to kind of narrow the range of the range of things that you need to check to some extent. If you have, for example, if you have some function. If you have, and it's got some number of inputs, and it's got some number of outputs, for example, there is to some extent a sense in which, if this is like a normal circuit, if you're trying to find, outputs for some given set of inputs, like I said before, if you're kind of generating a circuit and converting it into a SAT problem, you have to represent all the wires and gates inside of this circuit, and so actually you have you have some number of inputs, you have some number of outputs, but you also have this much larger set of kind of intermediate states. To some extent, you can kind of factor out the intermediate states and only just look at the inputs and outputs. And so, in this case, you have 4 inputs, 2 outputs. That's 6 bits total. That's 2 to the 6th, or 64 possible states. But it might be much larger than that actually on the inside. And so this is kind of a 2 to the 6th problem that is disguised as a much larger problem, right? And so to some extent, it's not all. You can have problems that look a lot bigger and a lot harder than they actually are, right? So now, if you have algorithms for actually trying to solve these kinds of problems, the kind of first main algorithm that I'm aware of that was used for this, other than just pure brute force, is something called DPLL, and DPLL is I forget what it stands for, but it's a bunch of different researchers' names concatenated together, right? And this is you have some state space, and let's say you have some 5-bit problem or something, right? And so you're trying to find some value here to that satisfies all of the every possible constraint. So you essentially do this kind of depth first search. You kind of treat this as a big tree. So you pick you have, as like a big decision tree. So you have, you guess what is the first value? Well, it's either going to be 0 or 1. Let's pick 0. Then, well, what we can do is we can check the next value. Is this value 0 or 1? We can pick 0 or 1, and we go down some branch of the decision tree. But then, as we're going, we check are all of our all of our constraints satisfied. So if we have some constraint that says that A is 0 or B is 1, well then as soon as we set 0, this first value, let's call this A to be 0. Well, then this clause is satisfied, and we can basically ignore it at that point. And so we have some set of we have some set of clauses, we have some set of constraints, and as we set variables, we can kind of start crossing them out as like, okay, this is already satisfied. But sometimes you have a situation where, so there are kind of two interesting cases. If you have a constraint that's, let's say A and negative B, A and not B, if you set A to be 0, well then this is then the only way that this clause can be satisfied is if B is because A is not equal to A. You can't rely on the A here because that's the clause requires either A has to be true or B has to be 0. If A is A is 1 or B is 0, if we set A to be 0, then the only way this can be satisfied is if B is also 0. And so then if we have that case, then what we can do is we can actually we can do something called unit propagation, where we can say that, okay, as soon as we make a decision about A that affects this constraint in this way, then we can actually infer that B has to also be 0, and so that allows us to cut off this whole branch of the tree. And if you're dealing with this problem where the size of the tree grows exponentially with a number of variables, being able to cut off branches like this, especially very early in the problem, cuts the search space down enormously. And so, especially as you have very, very large problems, this becomes a very big saving, especially, a very big optimization, especially if you have a lot of, especially if you can make a lot of those kinds of, you can prune a lot of those things very early. So that's called unit propagation. The other case is if you have some collection of constraints where for example, if we set B to be 0, and then we have some other constraint somewhere else that requires B to be 1, well then we have a contradiction. And so maybe we have A and B as another constraint. Well, this is if we set A to be 0 in both of these cases, then this constraint says that this constraint can only possibly be true if B is equal to 0, and this one can only possibly be true if B is equal to 1. That is a contradiction. There's no way of satisfying both of these constraints at the same time if A is equal to 0, and so this would actually imply that A must be equal to 1 if we have these two constraints. And so that means that if we run into a situation like this, then we have to backtrack and we say, okay, we have made a mistake somewhere in the series of variables that we've picked already, and so we have to backtrack to where we made that mistake and make a different decision there, right? And if we decide, if we backtrack to A, then now we have to pick that A is equal to 1. Maybe we have some other set of constraints somewhere else that now says, okay, actually this is incompatible. This is unsatisfiable because some set of constraints somewhere else requires that A is equal to 0. Well, now then we have some set of constraints that only work if A is 0, and some set that only work if B is, or if A is 1. And so then that would be unsatisfiable. There are no possible solutions for the whole thing, right? Or maybe we just have some, maybe we can actually kind of walk through the whole tree, make it to the end, and find something that does satisfy all of these constraints at once. So this is DPLL. This is from, I believe, the 70s or 80s, and this was kind of the standard way that a lot of people would solve these problems for a long time. On its own, this is not, this is a lot better than just pure brute force. Yes?
Yeah, when you're backtracking, like if you discover one of your variable picks is bad, you backtrack.
Yeah.
Is that done alphabetically sort of in order of the picks you've made, or is there like reordering of the tree? It's only that one that was wrong, so we'll only
Yeah. I believe classical DPLL does it generally in order, and then some variants will use a heuristic. For example, they will sort variables based on how many constraints there are. So you go with the most highly constrained variables. You pick from the most highly constrained variables first, right? And that generally is a nice heuristic that works across a lot of different problems. But there are many different variations of different types of SAT solving algorithms that people have come up with, and I'm sure there are some where you do have a little bit more flexible ordering of things. And in the case of the unit propagation, that is something where you can have variables that are much further down that you haven't made it to in this decision tree yet, where you can already narrow this down of like, okay, this variable that's like several, that's like maybe 100 levels down in the tree has to be this particular value, and so we can, if we've made the decisions that we have already, right? And so there is, you can come up with other algorithms that do a little bit more flexible ordering, but in the case of kind of classical DPLL, that's not something that really happens outside of unit propagation. Yeah.
So in this case, when you select a constraint or choose the variables, or you figure it out, do you assign certain values, and those values get played out and simulated at some point? Like how do you represent not only the variables, the earlier point in the beginning?
Yeah.
It's it's no longer the bits is just the variable.
Yeah.
It's the entire thread of the circuit. So then how do you do the representation of that as a value?
Yeah, how do you represent an individual value? I mean, you can do it as simple as, this variable is 0, it is 1, or it is unknown, right? And then you may have some extra kind of data structures for tracking which variables have been inferred through unit propagation based on which decisions earlier were kind of made based on that. Another interesting thing to point out that is maybe a useful kind of intuitive understanding is you can get these kinds of like information cascades where you have, if you have a bunch of kind of cases of this unit propagation, you can have something where one variable collapses, and then that interacts with some set of constraints where where you can infer that some other variables now must have specific values, but then those also, when they collapse down to a known value, those may also collapse other constraints, and so you can have these kinds of like information cascades where deciding a particular variable, in some particular context may collapse a large number of other variables, right? To some extent. So if you have something where you have like a normal P-style problem, a normal kind of problem where you are only kind of passing you're only passing inputs in one direction, and the output of a particular gate is always deterministic from its inputs. There are no cases where you can have like some superposition of possible outputs for some given input, right? This is something where as soon as you have all of the possible inputs, you can just propagate this. This does actually turn, you can just emulate this exactly with unit propagation, where as soon as you know both of these inputs, then all of these constraints in this gate propagate, and you already can determine the output of this gate, and then as soon as you that can, if you know all the inputs for the circuit, that can propagate all the way through the circuit, and you can compute it you can compute that very quickly, right? So to some extent, NP problems are you have some arbitrary collection of variables. There's some arbitrary kind of graph of constraints between them, and then you are kind of picking values for these variables, and then you can have these big kind of cascades where you pick this combination of values for these combination of variables, and it collapses a bunch of other state, and it kind of propagates out. And this is something where it can be very dependent on very specific cases. If, for example, you have like this kind of backwards AND gate that we were talking about before, where you have one input and two outputs. If you have something where, this is something where if you know that the input here is 1, well, then you already know that both outputs have to be 1. This is something that, this is a situation where this propagates very nicely. But if the output has to be, or if the input is 0, well, then this does not propagate nicely, right? Then you have a superposition of, there are 3 possible states here, and now this kind of blows up the state space of, okay, now there are 3 possible outcomes. To some extent, as you're kind of navigating through this big decision tree, you are going to kind of have to check all three of these states to some extent, unless you can rule them out as being incompatible with some other part of the circuit, right? So it is something where you pick a couple of variables and it can kind of collapse a large number of other things. If anyone is familiar with a little bit of game development and has heard of the wave function collapse algorithm, which is used sometimes in like procedural generation, this is actually very similar in a lot of ways, where you have kind of some collection of variables that can be in some number of states or some kind of superposition of states, and you have some set of constraints between them. Wave function collapse in particular is like you have a if you have like a game and you're trying to generate a level, you might have like some set of tiles, and you say like, okay, this tile here, or we don't know what each tile can be, but it can either be grass or it can be stone or something, or some combination of other things. And so each place is it can be grass, it can be stone, and you can kind of represent a superposition of these, and you can say like, okay, grass can be next to stone, but maybe there's some other there's like a wall or something, and a stone can't be next to a wall or something. And then if you know some combination of variables, you can if you have like a wall here, and you say grass can't be next to a stone, well, then that means that all of these squares around, or grass can't be next to a wall or something. You could say like, okay, all of these squares around the wall can't be grass, and so we can narrow that down, and then maybe then there's only one option left here, and so we can say that might be a stone or something, right? And that you can have if you can go online, you can find nice visualizations of this wave function collapse algorithm used in game development. But this is analogous and actually is it's probably NP complete. It almost certainly is. Yeah. Oh, I thought you had a raising. Yeah. So there are a number of other algorithms that people or kind of extensions to DPL that people have developed over the years. The one that really revolutionized the space and really kind of made people stop dismissing NP, or made the researchers in this field who are aware of these problems stop dismissing NP as purely exponential time and intractable in most cases, is an algorithm called CDCL. CDCL, or conflict-driven clause learning. And note the last word is learning. So there's some work going back to actually I think this is kind of getting to the point I was going to add to your question before about do we know all of the clauses? So conflict-driven clause learning. So there was some complexity theory work going back to I believe the 1980s or so. I want to say this is from Leslie Valiant and a couple of other people, I think, where they were able to show that if you have a learning algorithm, for example, and a neural network, and you try to train it on some cryptographic problem, right? You try to factor prime numbers or something, or you have like SHA-256 hashing algorithm or something. You have some problem that is assumed to be hard, and you try to train it on input-output pairs and ask, can the neural network learn to generate the inputs for this particular output? Can it break this cryptographic function? If you assume that these cryptographic problems are hard, then that means that, if you assume that they require an exponentially large amount of work in order to solve in the general case, then this is something where you would assume that even a learning, some fancy learning algorithm, deep learning, whatever fancy AI algorithms are out there, should still fundamentally require an exponentially large number of input and output pairs before it can generate that circuit, right? And so there's this observation going back to the 80s or so that actually machine learning and cryptography seem to fundamentally be opposites. Where if you have a cryptographic if you have some problem that is cryptographic in nature, or whatever properties of a circuit makes it function well as a cryptographic function, that actually means that if you have those kinds of properties in some kind of natural system, then that should actually be resistant to learning algorithms. So we have this conflict-driven clause learning algorithm, which came out which was developed in the late 90s. I believe the first paper on it was published in 1997, I believe. Though I think it was kind of being announced at some conferences a couple of years before that. But this is essentially the way that this works, roughly speaking, is you have you do your normal DPLL. And you're kind of wandering through this big kind of decision tree, and maybe you hit some kind of conflict or some kind of contradiction, and you say, okay, this branch, we can't go any further here. Well, then generally what you do with CDCL is you kind of walk back, you kind of analyze the graph a little bit. Because you have this big graph of variables connected by clauses, and you see, okay, what are the decisions that I made leading up to this, and is there some kind of constraint that I can add here, where it is redundant, it is equivalent to all the constraints that I already have, so it doesn't change the problem, but it works in a way where if it's structured in a way where it implies some unit propagation, where if A and B were both true, then that implies that C must be false in a way where it avoids this particular branch that I've taken here. Then essentially you are learning a particular case of I kind of gave the example before of like A and not B, and A and B. This is a situation where if A is equal to 0, then both of these, then this constraint says that B has to be 0, and this constraint says that B has to be 1. You've hit a contradiction. If you then run into this situation and you just say, okay, here's a new constraint that just says that A has to be equal to 0, otherwise we hit this inevitable contradiction, well then this doesn't change the problem at all. But now, if you are kind of wandering through the state space and you come across some situation again where you have to kind of re-guess A and B, well then you know automatically that A has to be 0 because you've learned that. And so you are kind of accumulating this knowledge about the problem, and this actually ends up being one of the biggest speedups this is basically the biggest speedup for SAT solving that anyone has ever found. And so it's interesting that it is a learning algorithm here that solves these kinds of problems. And it's also a discrete learning algorithm. There's no adjusting weights or anything. This is just adding these purely logical symbolic rules. There are also cases where you can have these kinds of SAT problems where you can have very large SAT problems. So SAT is something where you can have problems where you might have only a couple hundred variables or so, and it takes just forever to solve. and you can have another problem that has 100 million variables. And if you assume that this is exponential scaling, 100 million is just hopefully impossible. But actually, there's some cases where because these problems are so dependent on the structure of these constraints, you can have problems, real world problems. Where some SAT problem with 100 million variables might actually be something you can solve in a reasonable amount of time, right? As a very simple, trivial example, you could just encode a normal P problem, a normal polynomial time problem as just a SAT problem. You build some circuit, and there's no fancy, non-determinism going in here. You just pass the inputs, and you get exactly one output for that. You can encode this as a SAT problem, and that would be an example of something that is kind of easier to solve.
Charles?
Yeah.
These
Yeah.
general purpose SAT solvers
Yeah.
that we have now, how good are they at doing precisely that? Like if you throw them random things like sorting,
Yeah.
if you encode a sorting problem with a bunch of constraints, what kind of time do they do that in?
So I mean, it depends. It depends somewhat on exactly how you encode the problem. If you're doing sorting, for example, that's generally dependent on memory a lot, and memory is something that's a little bit trickier to and not particularly efficient to encode as circuits. But a lot of simple kind of circuit-based functions are generally fairly easy to encode. There are some cases where you can have some fairly straightforward problems that you can encode in these ways, but that can be solved. But there's also cases where, for example, if you try to if you have like a big multiplication circuit and you try to do A times B equals B times A. This is the commutativity property of multiplication. This is something that's taught in grade schools, right? But this is actually a property where if you build out a couple of multiplication circuits and check that they have the same they have the same input for every possible value. This is actually something that takes exponential time on a SAT solver usually, or at least with the SAT solvers that we generally have today. There are, like I said before, there are a number of different types of SAT solvers that people design that are kind of optimized for different types of problems. There are some SAT solvers that are designed just for random SAT problems, where it's just a random assortment of variables and constraints with not very much kind of regular structure to it. Those are actually a situation where CDCL generally fails and or generally is not very effective. And in those cases, that's something where doing stuff like random starts, where or random restarts, where you kind of just try a bunch of random you might kind of take kind of random paths through the state space, rather than just kind of check all the 0 values first or all the 1 values first. You kind of take some you kind of have like some random set of starting guesses and kind of try to work from there, or maybe you throw some parallelism at it, right? And run 100 cores all checking kind of a different path through the state space or something, right? There are a number of different approaches. There's also a lot of different ensemble approaches where you have solvers that are actually a dozen different solvers that are all using different heuristics, and they all run in parallel and try to find some kind of whichever one finds a solution first wins essentially. This is another interesting thing that people have generally found is that you can come up with really fancy heuristics, but actually in a lot of cases these simpler heuristics generally work better. And so if you have some because these problems fundamentally do kind of boil down to just brute force, just make as many guesses as you can. You can constrain the state space to some extent, and there are some cases where that works better than others. But generally speaking, if you can just make more guesses, that works better. And so if you have some really fancy, really expensive heuristic that tries to make better guesses, very, very often that is actually much worse than just a much cheaper, faster thing that just makes more guesses. Using some much simpler way of generating those guesses, right? Another specific thing that is kind of getting back to some of the kind of more abstract, strange things about SAT and about NP. I mentioned before that that there are a lot of different problems. Or there are a lot of different kind of properties of computation where you can define these linear hierarchies. You can say that, okay, if you have two computers and they both have they're both able to run for a finite amount of time, and one of them is able to run longer than the other, then the one that runs longer generally can can solve a wider variety of problems, right? If you have and the same goes for memory, and the same goes for a number of other things. But NP is actually a situation. NP is actually a property of computation where this does not actually seem to hold. I mentioned before that there are a number of different barriers to NP that people have found, where there's huge classes of techniques that people have shown are fundamentally incapable of answering this the P versus NP problem. The three of those are there was the Baker-Gill-Solovay theorem in 1975. That was showing that relativization techniques, where if you're trying to solve like the halting problem, for example, or a lot of other kinds of classic examples where you say that, okay, let's pretend that we have some magical function that can solve this particular problem. Is there some way that we can show that there's some logical contradiction, and this magical function can't possibly exist? That method is not capable of solving the P versus NP problem, according to the Baker-Gill-Solovay theorem. Then there was the natural proofs barrier, which was from 1997. This is probably the most interesting of the three, and this basically boils down to if you have some set of problems and you're trying to determine which of these problems are in P and which ones are in NP, right? Can you if you ask, is there some way of, can we frame this in some way where there is some linear metric, some kind of hierarchy where, there's like one variable, and we can say, is there some efficient, is there some computation that we can, some function that we can run where we can take each one of these values and map it onto some unambiguous point on this line, and then say like everything above this line is in NP and everything below this line is in P. The natural proofs barrier says that if P is not equal to NP, there is no possible algorithm you can ever come up with that runs in sub-exponential time that can reduce to this. And so you could also come up with some other way of like, okay, well, what if we can reduce it down to two variables or something, and then we say that like, okay, there's like some kind of complicated complicated curved line or something that we can come up with. And if whatever algorithm you use for computing this line takes sub-exponential time to compute, it is not capable of separating P and NP, assuming that P is not equal to NP. If it turns out that P is equal to NP, then actually you can do this. But this is an interesting case where essentially this kind of hierarchy, this kind of linear hierarchy that you get with a lot of other types of properties of computation is actually not something that is compatible with NP. And to some extent, and so another way of thinking about that is if you have like some state space. So another way of viewing NP, and maybe this is something I should have mentioned a little bit earlier, but NP is one of the kind of common ways of describing NP is it's a class of problems where you can, if you have a solution or a potential solution, you can verify whether or not it is a valid solution very efficiently, but finding a solution if you don't know it may not be as efficient, right? That's one of the more kind of easier ways of describing it. And so if you have a, if you're trying to do prime factorization, if you have p times q equals x, if you know what x is, and you know what p and q are, or if you have kind of guesses for what p and q are, you can just multiply them together very efficiently and check are they equal to x, right? And if you know what p and q are, that's a very easy thing to guess. If you don't know what p and q are, then that is much harder to guess, right? And it does boil down to basically just a lot of guess and check. Assuming p is not equal to np. The third barrier, which I will very briefly mention, I don't understand it as well as the other three, and this is a lot more recent. This was one of the people who worked on this was Scott Aronson, but this was the algebraization barrier. This was 2008, I believe, or 2007. This is essentially, there were a bunch of different techniques that people working on circuit complexity problems came up with, involving reducing some problem down to certain types of polynomials and showing that this particular type that like you have to have a certain complexity of polynomials, for example, in order to express some particular circuit. The algebraization barrier, my basic understanding of it is this whole class of techniques based on algebra that all of these circuit complexity theorists came up with is also completely incapable of dealing with P and NP. But essentially, part of what's going on with NP is, if you assume that P is not equal to NP, then what that means is, if you have some state space, how efficiently you can solve a problem here is dependent on where you start in the state space. If you know that there's a solution over here and you just get really lucky and you pick something that is in the solution space, you have found a solution right away, right? Whereas if you pick a solution that's over here and you kind of have some algorithm for kind of wandering through the state space, it may be a very long time, especially if the state space is very, very big, before you actually wander into something that has some solution. Another interesting thing to point out is you can have many solutions. You can have problems that have more than one possible solution, as I expressed here, right? If you have this backwards AND gate and the input is constrained to be 0, there are multiple possible outputs of this circuit. And so that is kind of where the non-determinism term comes from, of there are kind of multiple possible outputs for a given input, and it's not always, you can't always reduce it to just one obvious output for some given input.
So
Yeah.
will the variables be both discrete and non-discrete variables?
So there are. So I mean, you can do. I mean, most of the all of the kind of classic examples of NP problems I've seen are generally discrete. I mean, I think the technically yeah. I mean, it is generally discrete, and there to some extent, if you're trying to encode some continuous problem, well then you do kind of need an infinite amount of precision, and so that is kind of an infinitely large, infinitely complicated problem to some extent if you want to compile that down to gates and convert it into a SAT problem, right? So that is a little bit tricky to do that, to handle continuity there.
Has there been any work on characterizing solutions like as a distribution, where it's like you don't know the exact solution, but it exists inside this distribution?
So there are things. So you can. I was talking before about you can kind of build up these tables of if we have this set of variables, we can kind of say like, okay, these ranges of variables are valid and these ones are not, right? You can actually have. You could, for example, have a. you can take a SAT problem and you can solve a subset of it, and then you can build up some kind of table, for example, of here are all of the possible configurations of this subset of the problem that are all compatible with this, or that are all compatible with all the constraints that apply to these variables, and then whatever constraints you pick for these ones must necessarily be compatible with whatever these are. So that is another kind of a way of looking, interpreting this kind of a bit more visually is if you have some SAT problem and you divide it, you have some SAT problem and you divide it in half, where now it's essentially two connected SAT problems. You can, for example, have some table where we can think of this as like a two-dimensional table where there's some set of values here that are compatible. These are all of the kind of values that are valid states of this part of the problem. Subproblem A, and then there's subproblem B, and like these are the values that are compatible with that. Then you can actually show that you can kind of look at it from this perspective of you can kind of build up this kind of two-dimensional graph.
But this way, like all the probabilities are essentially like equal, right? It's not it's all equal. It's either zero probability of this or every value in the space that has equal probability of being a solution. But is there any sort of like simple answer, normal distribution, but obviously there's many other types of distributions. Is there like any work?
Yeah. I think there's kind of a variant of these there's a bunch of different types of kinds of problems that you can talk about in complexity theory. NP kind of boils down to what's called decision problems, but there are kind of variants. For example, there are counting problems where instead of saying, is there a solution to this problem or not, you can ask how many possible solutions are there to this problem, right? And counting problems are generally a bit harder, sometimes substantially so, but you can. I believe there are a number of algorithms that do kind of generate approximate solutions to counting problems, and maybe that's a little closer to what you're asking about. I'm not too familiar with more continuous approximations of them, although I don't remember the exact construction of it. And the exact derivation of it, but with this kind of particular kind of two-dimensional version of this problem, I do remember one time showing like, okay, if you know that like this variable is kind of in like this subset, if you assume that this variable is in this subset of the space, and you know something about these, how these variables are related based on some kind of graph like this, you can actually, I forget the construction for it, but you can actually construct something that looks a lot like Bayes' theorem. Like Bayes' theorem kind of just falls out of this in some particular ways, but I don't remember the exact construction of that. If you have this kind of two-dimensional plot here of the different subproblems, this is there are going to be generally unless these two problems are completely disconnected, if there are constraints kind of connecting these, well then what that means is here are all the these are all the solutions to A, these are all the solutions to B. This is kind of the product space of A and B, and all of the solutions that are compatible with both, all of these kind of colored spaces are the ones that are compatible with both of those at the same time. And then if you have some set of constraints, then generally what that's saying is, those constraints will reduce it to some subset of these, right? Maybe there's certain kind of chunks of these solutions here that just get canceled out by the constraints that you have, and there are others that might not be, right? But you can generally kind of break down these problems to some extent and kind of generate these you can generate kind of tables of, if we look at like this particular slice of the problem, we can see that like only like here, only like values that, only, whatever the solution has to be, it has to kind of fit into values in these table, in a table like this, if we only look at, these particular variables or something, right? Anyone have any questions? Is that clear enough? Yeah.
Oh, something a little bit earlier about the natural proof spin. I wanted to make sure
Yeah.
that, I understood. So basically it sounded like it boiled down to, were we able to like have the function where we have the line like you were talking about. If P does not equal NP, then actually finding that threshold cannot be done in a polynomial time.
Yeah.
Okay.
So there's a field called metacomplexity, which is how hard is it to tell, which is asking the question of how hard is it to tell how hard a problem is, right? And there was a result from just a couple of years ago. I don't remember who the researchers were, but there was a fairly recent result a couple of years ago where people were able to show that assuming the natural proofs barrier, then you can actually show that for any given NP problem, computing exactly how long it takes to solve, or even just the average amount of time that it takes to solve, is actually in general equivalent to solving the problem in the first place, or of similar complexity. So it is. And I believe the particular explanation of that is you can reduce this down to something called the minimum circuit size problem, which is if you construct some kind of circuit or some that takes in like a description of one of these SAT problems as an input, and you takes the state space of some SAT problem. How big is the circuit that can take some arbitrary configuration and or if you have some set of inputs and outputs for some SAT problem, can you have some function that can compute a solution, or can compute whether or not there is a solution? What is the minimum complexity, the minimum number of gates that you need to implement that function? And you can show that there are certain types of what are called one-way functions that are kind of the foundation of a lot of cryptography, where you have like some kind of random cryptographic key that just kind of looks like a bunch of random noise or something, and it kind of gets put into some function, and it spits out something that looks like a bunch of random noise, but this function is not very hard to compute, and so it's not actually random. It is pseudo-random, and so it's actually being generated by a much simpler function. And so if you have like the minimum circuit size problem, then you should actually be able to tell when something's actually random, where the circuit to describe it is actually extremely complicated and extremely large, or is it actually like one of these very small simple circuits that only looks very large and complicated, but that is actually much simpler, right? And so all of our cryptography depends on the assumption that you have these one-way functions, where you have these functions that are simple but look complex. And if you can tell those two apart reliably, if there's some efficient way of computing that, then that implies that P is equal to NP because of the natural proofs barrier.
Right, because you're
yeah.
the key itself.
Yep. And so.
One
Yeah.
related question is, because this is what truly denotes the complexity of this, right? Is it both the sort of variables, sometimes can be known unknown, discrete, some case unknown discrete, and or the number of variables that you're actually bringing in, and that obviously each new variable you're kind of resetting the possibilities.
Yeah.
What drives the core complexity here?
So I mean, kind of as we just described, determining the kind of true complexity of a problem is about as hard as solving the problem in the first place. But you can kind of constrain things somewhat. If you have a problem that is just like NP is a superset of P. So if you have some kind of normal like feed-forward circuit where all the gates kind of go in from inputs to outputs. This is some polynomial time circuit. As soon as you have all the inputs, you get all the outputs. You get the one exact output of it, right? That is something that is that's generally pretty easy to compute. If you have something that's a little bit more a little bit more complicated, well, if you have something where there's some number of inputs, there's some number of outputs, and there are some collection of gates in between, and there's no essentially the inputs and outputs are essentially kind of variables that are kind of untethered to kind of gates around them or anything. If you have something that where there are no kind of unknown, all the kind of values in the middle are all just the result of some kind of simple, or some kind of straightforward circuit like that, then essentially the complexity is only proportional to the it's kind of how many inputs plus how many outputs, 2 to the power of that is like the maximum size of the kind of true search space, and then you have some number of gates and wires in the middle that make it look a lot bigger than that, right? So there's a particularly kind of I'll kind of get to 2 interesting kind of constructions that I have found that I have not heard too many people talk about before. I've never heard other people really point these 2 things out. These are things I've found on my own that I think are very very interesting. So one of these I've published on my blog, and the other one I've told a few people about, but like this is something I found several years ago that I have found very insightful that I just have not published anywhere. So one of these is kind of a relationship to geometry in kind of a vague, abstract way. So, I mentioned before that NP is something. The P versus NP problem is very strange in that you have like these multiple different barriers that people have found where the problem is a lot. There are a lot of very strange things where we can prove that all of these different methods that we have are just incapable of solving it, and it's. It's a difficult problem in this respect. There is another type of there was a problem very well known for a long time, the Euclid's parallel postulate problem in geometry, where Euclidean geometry is based on these 5 axioms. You have the first 4 axioms which describe properties of points and lines, and then the 5th axiom says that if you have 2 2 parallel lines, these two lines will never converge. Will never converge or diverge. They stay equidistant, right? And this is a much more complicated. This is a much more complicated axiom than the other 4, and so for a long time people were kind of uncomfortable with it, and were wondering, is there some way that we can prove this from the other 4? This is a problem that took 2,000 years to solve. It was known to the Greeks, and it wasn't solved until technically the early 1800s. I believe it was either Gauss or Euler, very famous mathematician, discovered a solution to it, but decided that it was so heretical to mathematicians that even being widely considered as the greatest mathematician of his time, if he would have published it, he was afraid it would completely destroy his reputation, because mathematicians would consider it complete heresy. A couple decades later, some other mathematicians kind of independently discovered this, and eventually, kind of the cat was out of the bag. But eventually, what people eventually what people found was that actually this kind of assumption of that parallel lines stay equidistant is not actually valid, or it's independent. Yes, it's independent. There are essentially alternative geometries where parallel lines work differently. If you have a flat plane, then parallel lines do stay equidistant. But if you are operating on like the surface of a sphere and you pick 2 points, for example, 2 points on the equator and you draw kind of parallel lines, those do eventually converge at the poles. And so you can't actually have parallel lines on a, if you have parallel lines on a sphere, they do eventually converge. And then there's also hyperbolic geometry, which is much stranger, and is something that's not exactly straightforward to draw or anything. It is kind of analogous to kind of a continuous form of a tree, where essentially hyperbolic space, one way of thinking of this is if you have a point in a space and you ask how much volume is there if you have, if you draw like some sphere around, or some circle or sphere around the point of a certain radius, as you increase the radius, how does the volume of this sphere or this circle change? And so with Euclidean geometry, it is roughly the number of dimensions to, or it is the radius of the circle to the power of the number of dimensions, right? So if you have 2 dimensions, it's r roughly. It's proportional to r squared. If you have 3 dimensions, it's proportional to r cubed, right? If you have spherical geometry and you pick some point and you increase it, it will. If you make the radius big enough, it will eventually cover the entire sphere. All points on the sphere will be within a certain distance of that point, and so eventually, kind of with spherical geometry, everything. The distance is. Does eventually converge to a finite value, or the volume of a circle on a sphere converges to a finite value once it gets to large enough, to a large enough radius. And then with hyperbolic geometry, it's a bit stranger, where if you pick some point in hyperbolic space and you kind of scale the radius of a circle around it, the volume of the circle or sphere actually grows exponentially with the size of the radius. In the case of the kind of tree analogy, this is essentially asking how many nodes of the tree are kind of within a certain distance of this particular of some particular point. Well, as you make the tree bigger and bigger, the number of kind of points that are kind of in like a subtree, near that grows exponentially, right? So, it is, Euclidean hyperbolic geometry is kind of analogous in this particular way, and hyperbolic geometry has the property that if you draw parallel lines, they actually will diverge as they approach infinity. Yeah.
This is a beginner level question.
Yeah.
What defines what makes lines parallel? I guess for the
So
sphere, I could imagine you're gonna have 2 like parallel circles.
So it's, to some extent, that's actually the kind of angle between them. And so when you have kind of parallel circles, it's kind of subtle, but like there is actually like a difference in the angles there. And so there is some sense in which actually if you're working on the surface of a sphere, the only way that you can have something that is truly a straight line on the sphere that kind of corresponds to a circle around it is actually if the circle has like a full is actually the radius of the circle is actually equal to the circumference of the circle is actually equal to the circumference of the entire sphere. If you have something that there are ways of which you can kind of project kind of approximate versions to of like these spherical and hyperbolic geometries onto a Euclidean plane, and essentially what it turns out to be is like if you do that kind of projection, there are some cases where you can draw some kind of arc or something that looks like a circle, on a sphere or something, and there's some cases where it will look, when you do that projection, it turns into a straight line, and there's some cases where it turns into like a weird arc, and so I mean that's kind of getting deep into the nitty gritty details. That stuff is kind of unrelated to the NP part here, but kind of where I will I want to get back to the NP stuff, but this is a, the interesting thing here that kind of caught my attention initially was you have these cases where when you have Euclidean and spherical geometry, the kind of radius of a sphere, which you can think of if the entire space is some space of some space of solutions to a problem in some abstract way, then the volume of some space is equal to a number of possible solutions, right? And it's interesting that when you have Euclidean and spherical geometry, it is either a constant or a polynomial, and we separate P and NP by if you have some kind of if you have some kind of function that describes how much work it takes to solve a problem, can you describe this as with an exponential function, or can you describe this with some polynomial of where the largest it's x to the fifth plus 3x to the fourth or something, right? Where there is some maximum maximum finite coefficient on one of these terms, as opposed to being like 2 to the x or something, where x can be arbitrarily large or something. There's a distinct mathematical difference between exponentials and polynomials, and so that's kind of one of the ways that we kind of try to separate P and NP, and it's interesting how the kind of sets of values, if we're asking stuff in like the radius of a sphere, these grow polynomially in these two cases, but in this case it grows exponentially, which sounds kind of analogously to NP problems. And so like I said before, the parallel postulate problem took 2,000 years to solve, and that certainly was people certainly tried a very large number of different approaches. And one of the things that people tried to do to make the problem a little bit easier was they tried to find alternative equivalent axioms to Euclid's fifth axiom. If we find some different way of framing the problem, does that give us some different insight? And there's one in particular that is called Playfair's axiom, and it says, okay, we have a line, and we have a point that is on the line, and we have a point that is not on the line. And then we ask, how many lines are there that we can draw that intersect through this other point that never intersect this line? And it turns out that if you assume that you have Euclidean geometry, the answer is always exactly 1. If you assume that you are in spherical geometry, then the answer is 0. And if you assume that you are in hyperbolic geometry, then the answer is infinity, or if you're kind of dealing in some discrete versions of hyperbolic geometry, it is not. It can be some finite value that is greater than 1. Right, and this is interesting. This kind of caught my attention initially because this is actually kind of analogous to if we have some kind of normal P-style problem where all of the outputs are deterministically produced from all the outputs are deterministically produced from the inputs, where there's only one possible output that is compatible with one possible input. Then that is kind of analogous to Euclidean geometry in this way. But if you have something where there are multiple possible outputs, this is something that is more analogous to the Playfair's axiom equivalent for hyperbolic geometry, where there are multiple possible outputs. And it is peculiar that that in both of these cases where you can have multiple possible kind of outputs to this particular problem, or where you have this kind of non-deterministic, there are multiple possible lines that can satisfy this particular constraint. It ends up with an exponential blowup in the kind of size of these spaces. Now this is a very interesting kind of connection and similarity. I have not found too many very deep connections further than this, though I haven't particularly focused on this angle for a while. I am actually kind of, as I'm describing this, thinking of a couple of maybe angles that I could approach in the future with kind of coming back to this. But there's another.
So would you be applying, so clearly from a spherical to the hyperbolic?
Hey, could you get me more water? Yeah, thank you.
So how relevant then is the hyperbolic geometry?
It's. I think this is something where John Nash, the famous schizophrenic mathematician, he was once asked, why did you believe all of these schizophrenic delusions? And his answer was, well, they came from the same place as the mathematics. In many cases, if you observe like some peculiar connection or similarity in mathematics, there oftentimes is some deeper pattern and some deeper connection. It might not always be obvious. It might take centuries of work before someone finds out why that actually is there. But it's a very interesting connection where in kind of multiple different places where you have something where like the non-determinism here looks similar to the kind of hyperbolic version of Playfair's axiom, and in both cases they do end up with this exponential blow up in like the number of possible solutions, right? Thank you. So that's kind of I have a larger kind of thesis that I talk about sometimes on my blog. I'll write the if you want to go to my Substack and subscribe or something, I do write sometimes about, there are a number of different ways in which I think there are reasons to believe that there are very deep geometric connections, there are very, very deep geometric interpretations of computation that we have not discovered yet. And I think this is an area of research that should be getting a lot more attention, and there are way more connections. This is just kind of one of the interesting kind of geometric connections. Yes?
Are all polynomial problems learnable?
I mean, that's an interesting question. I'm not sure exactly on the details of that. I know there is a lot of work going back to the 80s or so on rigorously proving things about learning algorithms. I'm not sure about that particular question, but it does. I mean, I think it's perhaps something that is. There's some sense in which the conflict-driven clause learning that I described before, right? So to some extent, part of what makes that work very well is that if you have if you kind of come back to a similar point in the state space later on when searching through this problem, and it might have like some different combination of variables kind of before it, right? That influence it. How likely is it that you're going to take a similar path, right? And so that the next time you kind of encounter this combination of variables, right? And to some extent, that's if it turns out that those variables are very sensitive to a large number of other variables here in this problem, then generally that kind of extra set of clauses that you learned and added to the problem may actually not be may not generalize very well, where the next time you come across this problem, you might actually go through a very the kind of DPLL, CDCL approach may actually wind up going down a very different path in the state space. And so to some extent these kind of clauses that you were learning are almost like a way of understanding like how compressible is this state space. Are there kind of regular repeating patterns? If I kind of come across a similar part of the state space, dealing with the same combination of variables later, is it going to be reshaped by some other variables that are changed in a way that completely changes everything, and where all of my previous observations are kind of invalid, or do the observations generalize, and where there are many parts of the state space that all look very similar to each other, right? And it is. And so there is some kind of compressibility here, and I think that might be something that's more orthogonal here, but I'm not sure exactly. But I'll get to this other very interesting kind of thing that I have found that I haven't heard other people describe before. So if we have some, if we have all of our clauses, all of our constraints in a problem, we could ask, is there some function, or if we have some constraint, is there some way that we can, for example, well, actually, I'll frame this a little differently in a a little bit more of a high level perspective. This is, this method this thing that I've found is kind of a simpler model of something that looks a little bit like DPLL if you look at it from the right perspective. It's not as efficient as DPLL, and I don't think there's really a notion of kind of unit propagation in it, but it is something where you do make these like large jumps over the state space. So it's kind of somewhat approximating DPLL, but it's kind of a much simpler kind of toy version of the problem. And the interesting thing is that this looks surprisingly similar to a discrete form of gradient descent. So the way that you do this construction is you have all of these clauses, and for each clause you have if you have A or B or not C or something, then what you are doing is you're trying to have some kind of function that takes for this clause you have some kind of function that takes in the you have all of your variables across the entire problem, and you can interpret this as basically being a giant binary number. And then you have some that's essentially operating over some range in this state space from like 0 to the maximum version of this value, and the maximum possible point in this state space. And then you can ask, is there what is if you have some point that you're at in the state space, like right here, right? You can ask, okay, is this constraint satisfied? Or if it's not satisfied, what is the smallest possible value that satisfies this constraint that's greater than the current initial point, right? And so then what you can do is you can calculate this for every this in particular this for these simple SAT style constraints. This is something that is computable very efficiently, and it's it's very easily polynomial time, but it's something where if you can compute that value for every possible constraint, it's basically if x satisfies if we have our constraint as some function c, if x satisfies it, then then it just outputs x, and if x does not satisfy it, then it outputs some value greater than x that satisfies this particular constraint. And so if we then take, if we compute this function for every possible constraint, and then we take the maximum of all of those values, then what that does is that skips over every value that is incompatible with some, that you're skipping over some range of values in the state space, where you can show that this is the smallest possible value that could plausibly satisfy all of these constraints. It doesn't necessarily do that because essentially if you have some value where it's if you have some constraint that says, okay, the smallest possible value that can satisfy this constraint is right here, well then you know that every value between here and there must not be valid for that particular constraint, right? Yeah.
I was wondering, because we're coming up on 2 hours, I was curious about the application of this system to biological systems.
Okay. So I guess maybe there's definitely a lot more that I could go through with this talk. So I guess maybe I'll have to leave a number of things out.
So that's a constraint.
Yeah. Constraint for this particular talk. So the kind of biological application is something that's kind of analogous, kind of related to this particular thing that this particular construction. So I'll maybe kind of mention a couple of other things. So if you have another way of interpreting NP is that if you have some kind of function and you can compute outputs from inputs, or you can compute inputs from outputs. NP kind of does not care about time. And so in fact, actually, you can have, there is no reason at all why you actually can't have, for example, some collection of logic gates that go one way, and then some other collection of logic gates that go backwards, and you can connect these in some complicated way, and then you can ask, is there some way of satisfying all of these at once? So essentially this is a situation where NP essentially, P is a complexity class where time matters, whereas NP is a situation where you can actually have loops, and you can have nonlinear notions of time, which is very interesting. In particular, anyone who's familiar with digital logic knows that, probably knows that if you have something where you have two NOT gates that flow into each other in a loop, this is actually how a lot of computer memory works. And it is something where if you set one of these wires to a particular value, the other wire automatically is set to the opposite, and that kind of forms this feedback loop. And there's two possible, there's kind of two possible stable configurations where both wires are opposites. That's actually also kind of related to. I'll try to kind of connect this quick to quantum mechanics. There's way more that you could go into here, but quantum mechanics is essentially you have. NP problems are you have like these exponentially large. You can think of it as you have these exponentially large Boolean arrays of vectors of Boolean values, and it's a range of possibilities, and you're doing Boolean operations on them to kind of narrow the set of possibilities, and then quantum mechanics is you are doing operations on these complex probability amplitudes instead, but it's still exponentially large, and you actually get kind of analogous structures in there. So you can have situations where the stable states might be here and here, and this is 0, 1, 0, 1. So the stable states here are 0, 1, and 1, 0. And so, the states 0, 0, and 1, 1 are invalid. And so this is a situation where either variable can be in either state, but they have some complicated relationship where they can't both be, not all possible combinations of those are the same. This is mathematically exactly what, the probability equivalent of this is actually mathematically identical to superposition and entanglement, this is basically entanglement in quantum mechanics, and superposition is just like there are multiple possible states that have probabilities other than 1 or 0, right? And so.
So how does that work? Because here it's more like a binary system, right? So then in the quantum, it's not zeros and ones. So how do you account for the fractions?
I mean the quantum case is. You can have, you have some range of, every value in this exponentially large grid has some probability associated with it, and they all have to add up to 1, basically, right? There might be a large number of them that are zeros. There might be, a number of other things, right? It's similar kinds of operations, but you're operating over probabilities instead of possibilities. There is the difference where, in quantum mechanics, the probabilities all have to add up to 1, whereas with NP, you can have any arbitrary number of solutions. Every possible value could be a valid solution. No possible value could be a possible solution. You can have something where there's basically a 0% probability of there being a solution in a particular NP problem. This is a situation where kind of the quantum the quantum case actually kind of breaks down a little bit. And in fact, one of the kind of, so there's something in quantum computing called quantum compilation, where you can take some kind of NP circuit and compile it down to an equivalent quantum algorithm, and you can run that algorithm, and it encodes the solution set to the NP problem, except that because the probabilities can be are like these complex numbers, actually, it's actually the probability, whether or not a value is actually a valid solution actually gets encoded in the phase of the complex number as opposed to the amplitude, which is not actually, or it gets, I believe it's encoded as like the whether it's a positive or a negative probability, which is indistinguishable when it's measured. And so it turns out that that's actually something where you can do the quantum stuff, but the solution ends up actually being encoded in something that is completely independent of whether or not it's observed. And so then there is Grover's algorithm, which can then kind of convert this unobservable state of the wave function into an observable state. But that takes exponential time, so you actually get no speed up on the quantum computer. But to kind of connect to the biology connection, this is something, so this is an interesting connection that I've noticed. So if you, if you have, if you have these circuits and they are, if you have some kind of circuit that has some kind of feedback loop in it, this is something that you can encode in NP that you cannot encode in P, right? So, and so, if you have, if you are actually trying to solve, the NP version of this, this is actually equivalent to asking, are there any fixed points here? So, if you have some function that's f of x, and you're trying to ask, is there some value f of x such that I put in x and I get x back? Where if I were to apply f to x an infinite number of times, I always just get x back, right? This is actually an NP problem. In fact, this is NP complete. You can reduce any problem in NP down to finding a fixed point for a particular function. In fact, you can actually show that that's related to the kind of discrete gradient descent thing that I found earlier. So if you have like a cell and it contains a bunch of chemicals and they're all interacting, you can think of that as a very elaborate function. And if you ask what are the equilibrium states, that corresponds to what are the fixed points. What are the points where, what are the configurations of the different chemical distributions in the cell where, once it gets to this state, once it gets to this configuration, it is stable in this configuration and doesn't want to change to a different configuration, right? And so that means that actually, if you have sufficiently expressive, proteins, which protein and cell interactions are definitely expressive enough for this. If you just ask what are possible stable configurations of chemical equilibria in a cell, then this is actually something that is NP complete. You can encode any arbitrary NP problem. You can encode any arbitrary constraint problem as some collection of chemicals trying to reach equilibrium, and the specific concentrations of each chemical at the equilibrium encodes the solution to your arbitrary constraint problem. Now, it may take a very, very long time to reach that equilibrium point, but it's a very interesting, that's one particular thing here. Now, if you kind of connect that to evolution, there's a lot of cases where biology creates like these very elaborate systems from surprisingly simple combinations of genes, and on one hand, that is something where if you consider that as essentially if you have a problem that is if you have some kind of optimization problem, then some simple set part of what kind of makes NP hard is that if you have some problem with some set of inputs, or some problem with some relatively small combination of constraints. In the worst case, the actual description of the solution space may actually be like exponentially hard or exponentially complicated to describe kind of directly. And so it can be, you can have a relatively simple system that generates this extremely complicated space of possible solutions, where if you were to describe it kind of constructively of like, this point is here, this point is here, this point is here, it would take an enormous amount of complexity, whereas actually you can generate that enormous amount of complexity from a much, much smaller system. And that actually corresponds very well to that corresponds very closely to you can take these you can take some arbitrary constraint problem that may be the set of solutions may be very, very complicated, and you can generate some relatively simple description of all of the constraints that in some sense encodes this very complicated solution space, right? And so you can have very complicated systems that optimally solve some arbitrary constraint problem in something that is proportional to the set of constraints, as opposed to the being proportional to the complexity of the resulting product of that. Right, and so in some sense, if you have a cell, there might be 1 billion chemical reactions happening every second, and so in some sense, this is actually every one of those billion chemical reactions is essentially some computation that is going into kind of brute forcing this exponential kind of gradient descent kind of problem, and so there's a lot of very interesting kind of connection. The cells are kind of the cells in your body in this kind of model are essentially these constraint solvers where every single chemical reaction is contributing to this kind of brute force search through this space, and it can solve these very complicated constraint problems fairly quickly. Now, of course, you can still define constraint problems that a universe full of cells could not solve in any reasonable amount of time. And so there's still going to be problems where you may have to kind of encode the body contains like the genome contains like body plan genes where you tell it like, okay, there has to be like this particular limb here and this particular limb here, and you could imagine like, okay, you describe some abstract set of constraints of like, here is the range of all possible body plans, and you find the optimal one given these kind of environmental constraints or something, which you can also factor in environmental constraints. If there's some chemical reaction from something that the cell absorbs from outside, or there's like some light, this is like some cell in the eye or something, and light hits some molecule in here and causes some chemical reaction. That can be like an input to one of these circuits, and so the chemical reactions can respond to the outside world and can compute things that are optimal or satisfy some set of constraints relative to the inputs from the outside world, right? This is something that is very, very easily computable if you make these very, very basic assumptions about how cell chemistry works from a computational perspective, right? But it also means that if you have there's kind of a question that shows up a lot in biology of like, how do you get very, very large amounts of complexity from kind of gradual accumulation of mutations? And what this kind of implies is that actually, if it's this constraint problem, then every constraint basically you have some state space, and some random configuration of cells could land in some point in the space, right? And maybe that's a good point, maybe that's a bad point, right? But then if you have these kind of constraints that you add, they will kind of every constraint basically reduces the set of valid equilibrium points. And so if you have a point that's outside of this, then if you then kind of through the equilibrium, it will kind of gradient descent its way into one of the valid points. And so if you have some constraint problem that has a very large number of constraints, then actually if you only have a subset of those constraints, there is actually a decent, there is actually some probability that you will wander into those just by one of the solutions just by random, basically, right? And so every time you add some new constraint, it actually kind of shrinks the actual solution space, but you could kind of pick some initial point that just kind of wanders in there by random. And so that does actually create kind of a smooth, if you're just adding more and more constraints, that actually does create kind of a smoother path where you could actually, that could potentially explain one of the ways in which very complicated systems can evolve more efficiently than we might presently assume. Yeah.
So my understanding is that like the tools for measuring intracellular dynamics have gotten radically better in like the last like 1.5 years, and I think a lot of the pressure to even develop those tools comes from applying ML to bio.
Yeah.
And it's interesting to think about this as both a driver. If you can kind of like prune likely cellular interactions in a deep learning model, based on things that you never observe happen once you're able to track millions of them. That seems like both like very useful for training these models and also like further, I forget what the algorithm was, the first or second one you talked about, that essentially says like, okay, like if this is a non-viable result, we're gonna prune it from any, and go back. Like that seems like even better confirmation than maybe one of the larger systems that you can actually come up through that in.
Yeah, another, the kind of gradient descent approach that I mentioned before, there are some interesting other kind of interpretations of it that you can give. One of them is that if you were doing error correction in if you're talking about error correction algorithms, there are actually all error correction algorithms basically boil down to you have some space of possible values, and then generally you have like some kind of lattice or some other kind of subset of points that are considered valid. And then if you have some kind of error in here, it kind of kicks it off off of one of the valid points, and then you have some function that kind of maps the invalid points to the nearest possible valid point, right? And there's a sense in which each one of the functions that I described for the clauses is very much of the very, very similar and effectively equivalent to this kind of approach. And so you can also actually think of it as it's something that looks a lot like a discrete form of gradient descent, but it also looks like you have a bunch of different parallel error correcting algorithms that all have to kind of converge onto some common point. There's a number of different interpretations here, and it is like, okay, there are and then there's another way in which you can kind of interpret this, which is that like, okay, you have some kind of set of possible points and they all get mapped to the same point, right? But then you might have many different points that also kind of get mapped down, and then these all kind of get mapped down to another single point, and you can get like these kind of complicated trees, and or sometimes they only get mapped down to a single point or a much smaller number of points, right? So these trees can be fairly irregular, but you can also kind of
Just wanted to say we're over 2 hours.
Okay.
At this point, so maybe let's take a few more questions and then we can hang out for a while.
Yeah, there's maybe like one more thing that I do want to kind of quickly mention, which is, so there are these complexity classes, and you can talk about P and NP, but there are actually some very interesting kind of generalizations here. So one way that you can think of NP is you have some polynomial time function f of x, and you do an existential quantifier on it, which is basically saying, is there some value x such that f of x is true, right? Now, there's also another complexity class called co-NP, which is kind of the inverse of NP in some ways, but this is essentially equivalent to a universal quantifier, which is saying, can I prove that every possible value of x, for every possible value of x, f of x is true, right? Now, if you have a bunch of quantifiers in a row that are all identical to each other, a bunch of existential quantifiers, a bunch of universal quantifiers, there's a way in which that's kind of equivalent to just having one that just operates over a much larger variable, a much larger number of bits. But if you have kind of alternations of them where you say like, okay, for all values of x, there exists some value y such that f of x and y is true, right? This actually does not fit into either of these, and so this actually requires another. So NP is equivalent to this, co-NP is equivalent to this. This is a different complexity class entirely, and then you can just add an arbitrary number of these quantifiers at the beginning of this. So this actually, so you can describe a bunch of complexity classes. So there's NP, and then there's P, and there's co-NP, or there's NP and co-NP, which are both supersets of P, and these correspond to if you have one quantifier. But then if you have two quantifiers, then there are a bunch of additional complexity classes. We'll just do. These are generally like sigma. I think there's like some extra symbol some people throw in here, but there's like sigma and pi 2, and sigma and pi 3, and sigma and pi 4. And these form this kind of like infinite hierarchy of complexity classes that are generalizations of NP and co-NP. And these are some very the point of this is like there are a lot more complexity classes than just NP and co-NP. And in fact, if you extend the hierarchy infinitely, then you get up to then you actually get, this is all called the polynomial hierarchy. The kind of infinite limits of the polynomial hierarchy is equivalent to P space, which is the complexity class of all possible problems that can be solved with a polynomial amount of space, but potentially some unbounded amount of time. And then there are other complexity classes beyond that: x space, x time x space, RE, and so on. But the polynomial hierarchy describes an enormous range of possible problems. In fact, you can reduce basically any conventional optimization problems to there exists some value such that for all value x such that for all values y f of x is less than or equal to f of y. Right? This definitely falls into I believe this complexity class right here, and so that's basically where actually I think it's this one here, where all optimization problems basically land here as opposed to NP. And so there are other complexity classes going up. There are things like QBF solvers, quantified Boolean formula solvers that can solve arbitrary values in the polynomial hierarchy. So there are even more complexity classes here that we have not explored, right? There's this whole range of basically, humans engineer things based on what we understand, and when we have, and I think we stick to P because there are a lot of things in there that we understand very well, whereas there's a lot of really strange things that are going on in NP. I don't think I really got a chance to fully explain a lot of them. I hope I kind of conveyed some of that at least, but there's a lot of very, very strange stuff going on in NP, and that we don't really have good ways of reasoning about, and we don't really have good, I think they are potentially very useful things. Clearly, I think I made a decent case that biology is using this. I don't think we have time, but there's cases I can make about neural networks using this to some extent. The basic argument is that if we have some problem that we don't know how to solve by more conventional means, there's nothing saying that the problems that we want to solve are all necessarily in P. And so a lot of them may actually be in NP. There are arguments about particular, for example, GANs and similar kinds of generative adversarial networks are essentially you're trying to compute a function and the inverse of that function, which is definitely is like an NP style problem where you have kind of forward and backward time in a certain respect. And so it is, there are problems where you can make a pretty compelling argument that I think that certain problems are in NP that neural networks are solving, and that does line up pretty well with a lot of these scaling laws that people observe, where these problems grow have exponential training data or time requirements to converge to linear improvements in performance. And so my kind of broader point of this is there's a lot of very strange algorithms out there that we have not discovered yet, and they very clearly have a lot of bizarre properties, and if we can try to understand them, we will gain a much wider variety of tools. Yeah?
Do you think P versus NP is fundamentally about the relationship between time and information?
There is a yeah, I mean, yes, I think that's actually a very good way of putting it. There is, it is to a very large amount about hidden information. If you know some kind of secret, this is the foundation of cryptography. If you know some secret, it gives you essentially exponential. You can construct problems that have this kind of cryptographic structure where if you know where the solution is, that gives you exponential leverage over computation, right? If you can devise a cryptographic problem where if you have a computer the size of a red blood cell that encodes a cryptographic key, there are problems that it can solve that a computer the size of a galaxy cannot solve in a reasonable amount of time, right? I think that is. That would be a long explanation, but I think there are very serious implications for things around superintelligence that where kind of a lot of conventional ideas about what AI, the future of AI and superintelligence looks like, actually are incompatible with P not being equal to NP. Where actually, if you have secret knowledge, you have an exponential advantage in situations where that knowledge is relevant over some arbitrary amount of computation. And so and I think that corresponds well to the fact that the way that we improve these neural networks is by just giving them more information, right? And if you hit against the limits of the accumulated human knowledge, then eventually it's not easy to kind of go beyond that. And I don't think just throwing more compute at the problem is actually something that really works or is something that, I mean, theoretically it would scale exponentially, but it doesn't take a very big exponential problem before you exhaust all of the computing resources of the observable universe to solve a relatively small problem. But overall, I think there's a lot of really strange. This shows that there's a lot of really strange algorithms. Computing is less than a century old. We are in the very, very, very early days of computing. I think a lot of people are not comfortable with that and want to assume that the AI will kill us all in 5 years and we are at the end of history. But I think this suggests that there is a very, very long future of very strange things that we have not discovered yet. And so that's kind of, I guess, my kind of broader point. Does anyone have any more questions?
Thank you, Charles.